There is a property of prime numbers, simple enough to state in a single line, for which we know exactly two examples. 2. In the entire infinite span of the integers, after a century of computer search reaching into the 100 quadrillions, we have found exactly two prime numbers with this property. The first one is 1093, found in 1913 by a German mathematician named Waldemar Meissner. The second one is 3511, found 9 years later in 1922 by Nicolaas Beeger. Since then, nothing. For 103 years, mathematicians have searched. Computers have been pointed at this problem. Distributed computing projects have ground through more candidate primes than there are atoms in a grain of sand. And the count is still 2. We do not know if a third one exists. Heuristic arguments, back-of-the-envelope probabilistic reasoning, suggest there should be infinitely many, but we cannot prove there's even a third. The next example, if it exists, lies somewhere beyond 10 to the 17th, or it lies nowhere at all. These two primes are called Wieferich primes. The property that defines them sits at the intersection of three deep areas of mathematics: Fermat's last theorem, modular arithmetic, and the way the integers behave in their 2-adic completion. This is the story of the two loneliest primes in number theory, and of the deep theorem that gave them their name. To understand Wieferich primes, we need to start with one of the oldest theorems in number theory. Pierre de Fermat, 1640, wrote a letter to a colleague about a pattern he had noticed. For any prime number p, and any integer a not divisible by p, the value of a raised to the power p minus 1 when divided by p leaves a remainder of 1. In compact notation, a to the p minus 1 is congruent to 1 mod p. For p equals 5, a equals 2, 2 to the 4th is 16, which is 15 plus 1, which is 3 times 5 plus 1. Remainder 1 when divided by 5. The theorem holds. For p equals 7, a equals 3, 3 to the 6th is 729, which is 104 times 7 plus 1, remainder 1. This is Fermat's little theorem, and it is one of the foundational results of elementary number theory. It is the engine behind most modern primality tests. Every time your phone confirms a TLS connection, it is running an algorithm whose correctness depends on this exact theorem. Now sharpen the question. Fermat's little theorem says that a to the p minus 1 is divisible by p, for any prime p. Sometimes, though, that quantity is divisible by something more than just p. It might be divisible by p times 2, or p times 3, or p squared, or even higher powers of p. When does a to the p minus 1 get divisible by p squared instead of just by p? This is a more refined question. For most primes p and most integers a, this doesn't happen. The quantity is divisible by p, but not by p squared. But occasionally it does happen, and when it does, we say that p is a Wieferich prime to base a. The specific case a equals 2, the simplest case, where we are testing whether 2 to the p minus 1 is divisible by p squared, gives us the original Wieferich primes. The classical case, the one we will focus on. 2 to the p minus 1 congruent to 1 mod p squared. That is the entire defining equation. And among all the primes ever tested, only 2 of them satisfy it. The 2 primes we are about to meet are named after a German mathematician named Arthur Wieferich, who proved a theorem in 1909 that gave these specific numbers their importance. Wieferich was 25 years old. He was writing his doctoral thesis at the University of Münster on Fermat's last theorem. The conjecture, famously stated by Fermat in 1637, that the equation x to the n plus y to the n equals z to the n has no positive integer solutions for any exponent n greater than 2. In 1909, Fermat's last theorem was still open. It would remain open for another 85 years, until Andrew Wiles finally proved it in 1994. But Wieferich, in 1909, proved a partial result. He showed that if a particular case of Fermat's last theorem held, specifically what is called case 1, where none of the 3 integers x, y, z are divisible by the exponent p, then the prime p had to satisfy a strict arithmetic condition. Namely, 2 to the p minus 1 had to be divisible by p squared. In other words, if Fermat's last theorem case 1 was false for some odd prime p, then p had to be a Wieferich prime. This is a powerful constraint. It transforms the question, is there a counterexample to Fermat's last theorem case 1, into the question, is there an odd Wieferich prime? And we don't have to find every possible counterexample, we just have to check the Wieferich primes. In 1909, no Wieferich primes were known at all. Wieferich's theorem reduced Fermat's last theorem case 1 to checking a tiny set of specific primes. Beautiful, powerful, and impossible to use, because nobody could find any Wieferich primes to check. The search began. 4 years after Wieferich's theorem, in 1913, a German mathematician named Waldemar Meissner found the first one. Meissner checked candidate primes by hand. There were no electronic computers. There were tables of powers and modular arithmetic, and there was patience. He worked through small primes one at a time. For each prime p, he computed 2 to the p minus 1 divided by p squared and checked the remainder. For p equals 3, 2 to the second is 4. 4 minus 1 is 3. 3 divided by 9 is 0 remainder 3, not Wieferich. For p equals 5, 2 to the fourth is 16. 16 minus 1 is 15. 15 divided by 25 is 0 remainder 15, not Wieferich. For p equals 7, 2 to the sixth is 64. 64 minus 1 is 63. 63 divided by 49 is 1 remainder 14, not Wieferich. For most small primes, the calculation produces a residue that has nothing special about it. The check fails. Meissner worked through hundreds of primes, then thousands. At p equals 1093, the residue came out to 0. 1093 is a Wieferich prime. 2 to the 1092 minus 1 is divisible by 1093 squared. The first explicit example. This was published in the Sitzungsberichte of the Berlin Academy of Sciences. It was the first concrete instance of Wieferich's theorem in action. Mathematicians could now use the constraint productively. The community immediately tried to find more. Hand calculation continued. For the next 9 years, no second Wieferich prime turned up. Many wondered if 1093 was a one-off, an anomaly in the integers with no companions. Then in 1922, the next one appeared. Nicolaas Beeger was a Dutch mathematician working at the University of Amsterdam. He continued where Meissner had left off, checking primes one by one through hand and increasingly mechanical aid. He reached 3511. The check passed. 3511 was the second Wieferich prime. That was the last one anyone has found, in either direction. Let that settle. Since 1922, computers have improved from rooms full of vacuum tubes to silicon chips packing billions of transistors. We have built distributed computing networks, GPU-accelerated number theory libraries, optimized modular exponentiation algorithms. We have searched every prime up to 10 to the 17th, that is, every prime up to 100,000 trillion. In all of that, no third Wieferich prime has been found. A typical recent search effort, PrimeGrid's Wieferich Search, a distributed computing project running on tens of thousands of volunteer computers, has tested every odd prime below 10 to the 17th. They confirmed both 1093 and 3511. And they found nothing else. We can think of this concretely. If you write out 2 raised to the p minus 1 for every prime p in the range 1 to 10 to the 17th, and divide each one by p squared, the remainder is 0 in exactly 2 cases. The 2 we know, and nowhere else. If a third Wieferich prime exists, it is larger than 10 to the 17th. There are infinitely many primes above that bound, of course. But the third one, if it exists, has so far refused to reveal itself despite 100 years of looking. So we have 2 questions. Why are these 2 specific numbers, 1093 and 3511, Wieferich primes? And how many more are there? To both questions, our answer is essentially, we don't know. There is a way to reason about how many Wieferich primes there should be. Take a random prime p. The value of 2 to the p minus 1 mod p squared can be any number in the range 0 to p squared minus 1. Well, almost any number. It has to be congruent to 1 mod p, which restricts it to one of exactly p possibilities. Of those p possibilities, exactly one of them is the value 1, meaning 2 to the p minus 1 equals 1 mod p squared, which is the Wieferich condition. So heuristically, treating the residue as random, the probability that a given prime p is Wieferich is roughly 1 over p. If we sum this over all primes, using the fact that the sum of 1 over p over all primes up to n grows like log n, we get a rough estimate that the number of Wieferich primes below n is approximately log n. For n equals 10 to the 17th, log n is about 3.7. So under this heuristic, we should expect roughly 3 or 4 Wieferich primes below 10 to the 17th. We have found 2. Either we are slightly unlucky on the count, or the heuristic is somewhat off. Either way, the estimate suggests there are infinitely many Wieferich primes overall, with the count growing extremely slowly. But heuristic is not proof. Nobody has shown that there are infinitely many Wieferich primes. Nobody has shown that there is even a third one. The argument I just gave assumes the residues are random, and they are not random. They are determined by deep arithmetic structure that we don't fully understand. This is the modern state of the question. We have a guess that says infinitely many. We have no proof. We have 2 examples. After a century of computation, that's the entire picture. The Wieferich condition has cousins. Many of them are equally mysterious. First, the obvious generalization. Wieferich primes to base a. Instead of testing whether 2 to the p minus 1 is congruent to 1 mod p squared, we test whether a to the p minus 1 is for some other integer a. For each base a, there is potentially a different list of Wieferich primes. Some bases have several known, others have 1. The base 2 case has the 2 we have been discussing. Second, Wieferich pairs. A Wieferich pair is a pair of primes pq where p divides q to the p minus 1 squared and vice versa. Only a handful of such pairs are known, all with both primes small. Third, Wall-Sun-Sun primes. These are primes p such that p squared divides a certain Fibonacci-related quantity. Specifically, if f denotes the Fibonacci numbers, a prime p is Wall-Sun-Sun if f sub p minus the Legendre symbol of 5 over p is divisible by p squared. How many Wall-Sun-Sun primes do we know? 0. Not 1. Despite a heuristic argument identical to the Wieferich heuristic predicting infinitely many of them, no one has ever found a Wall-Sun-Sun prime. We have computer searched every prime up to 9 times 10 to the 17th and found nothing. This pattern, heuristics predicting infinitely many, computer searches finding either 2 or 0, is bizarrely consistent. It suggests there is some hidden arithmetic structure preventing these primes from being common. We don't know what that structure is. Fourth, the Wieferich condition relates to a deeper concept in p-adic analysis called the Fermat quotient. For prime p and integer a, define the Fermat quotient q sub p of a as a to the p minus 1, all divided by p. This quotient is an integer. A Wieferich prime is one where the Fermat quotient of 2 modulo p equals 0. The behavior of these Fermat quotients connects to the way the integers behave in their p-adic completion, the alternative number system where instead of decimals getting smaller, increasing powers of p get smaller. The structure there is rich and not fully understood. The Wieferich primes might be deep regularities of this p-adic structure, or they might just be chance occurrences that happen to satisfy a coincidence. Mathematicians do not have the tools to distinguish these possibilities yet. Let's step back. We have a question. How many prime numbers have a specific simple property, definable in a single line of modular arithmetic? The answer, after 103 years of mathematical and computational effort, is at least 2, possibly more. We don't know. The 2 we know are 1093 and 3511. This is unusual. Most simple questions in number theory have either many known examples or strong reasons to believe in their non-existence. The Wieferich situation is uniquely uncomfortable. We have just enough examples to know the question is meaningful. We have far too few to draw any conclusions. There is something philosophically jarring about this. The integers go on forever. The pattern that defines Wieferich primes is short and decidable. If the heuristic count is right and there are infinitely many, they hide so far apart from each other that we cannot find a third in any reasonable amount of computational effort. If the heuristic is wrong and there are finitely many, we cannot prove it. The state of the Wieferich problem is, in microcosm, the state of much of modern number theory. We have computational evidence, we have heuristic arguments, we have connections to deeper structures, but the bridge from heuristic to proof remains uncrossed for problem after problem. The Goldbach conjecture, the twin prime conjecture, the Riemann hypothesis itself, all of these have similar character. Strong empirical evidence. No proof. The Wieferich primes are not famous like those problems. They sit in a quieter corner of number theory, kept alive by a small community of mathematicians and a long-running distributed computing project. But they tell the same story. The integers are an old structure. We have been studying them since recorded mathematics began. We are still finding open questions with simple-to-state answers that nobody can answer. The first Wieferich prime was found in 1913, the second in 1922. The third, if there is a third, may not be found in our lifetimes. What other simple-to-state arithmetic questions live in this in-between state where we know almost nothing? Drop your favorite in the comments. We have several more queued up.